we will now discuss how we can get the matrix elements. First we will look at how to get the matrix element H of the Hamiltonian region 2 H2 I comma j, and this one because we have got spheres inside, that is like I have said before that we have a cell and then we have a sphere, and this is region 2 and this is region 1. So what we can do is, in order to evaluate H2ij, we can take it as integral over the whole cell, this is chi APW of I star H2 chi j APW over the whole cell, and then subtracting from it the integral over the region 1, that is over region 1 chi I star APW, of course, H2 chi j So for region 1 it is pretty simple, that is if we integrate over the region 2, then what we will get is integral, because it is a plane wave in because chi APW that we are taking is a plane wave over the entire cell, we have integral over cell e to the minus I k I dot r minus del squared minus e to the I k j dot r d cubed r will just give me k j squared minus e delta I j, and this is multiplied by the cell volume, because normalization of the plane waves is with respect to the cell volume. Now in region 1, if we want to calculate the same integral, then we are looking at Hij minus E delta 2 Ij over the Newth sphere is what I am trying to calculate, over the Newth sphere. So this I can actually write it as kj squared minus E times e to the I k j dot r nu times integral e to the I k I j e to the I k I j dot rho times d cubed r, because r is equal to r, this is k I j, r nu plus rho. So now let us see how we can do this. Integral over the sphere e to the I k I j dot rho d cubed r, we can actually write it in the form which is integral 0 to s nu rho squared d rho, actually d rho I can actually put it later on, better that way, times integral 0 to pi sin theta d theta e to the I k I j rho cos theta is what I have, and this multiplied by a factor of 2 pi coming from integration over the phi part. This is a pretty simple integral to evaluate, because all you need to do is substitute for rho cos theta and integrate over d theta, and then I have an integration over d rho. Okay, if I were to do this, is quite easy to show that this quantity is going to be 4 pi s nu squared j1 kij s nu divided by kij. That j1 kij s nu comes because there is a rho which cancels this rho, and then you have a integration of rho times a trigonometric function, which is actually the integral representation of the Bessel function of order 1. So actually j1 x, you will notice, is nothing but sin x minus x cos x by x squared. And with this, if I use this one and substitute for my hij minus E delta ij in the plane wave part, over both 1 and 2 as the following. This can be written as kj squared minus E times V times delta ij. V is the volume of the unit cell, minus 4 pi times sigma over nu s nu squared j1 kij s nu divided by kij times e to the I kij dot r nu e to the I kij dot r nu times g nu ij. And this g nu ij is the quantity kj squared minus E times j1 kij s nu upon kj minus of sigma over L is equal to 0 to infinity. I will show you how I get this term. 2L plus 1 PL Ki dot Kj JL Ks nu Ki S nu JL Kj S nu JL Kj S nu into RL prime S nu divided by RL S nu minus Kj JL prime Kj S nu divided by JL Kj S nu. Now, how do I get the surface term? The surface term I got in the following fashion, because this whole thing comes from the surface term, and the surface term, how did we evaluate? So, I will just sketch how we evaluate the surface term. So, on the surface, chi2i is equal to chi1i. So, the one that involves the difference between chi2 and chi1, that will not contribute, and the surface term contribution only will come from the quantity which corresponds to chi2i plus chi1i is the only thing that contributes, and this is given by 2 into 4 pi, because I am assuming that we are doing the expansion of the basis set in terms of the spherical harmonics. So, I will have this times r nu times sigma over L is 0 to infinity sigma over m equal to minus L to plus L I to the power L JL KIS nu times YLM into YLM star Ki angular part, then YLM rho the angular part. So, this is what chi 2 I plus chi 1 I, and del by del rho chi 2 I minus chi 1 I is actually given by 4 pi e to the I k j dot r nu. This seems to be this is the j I k j dot r nu times sigma over L is equal to 0 to infinity, the terms that are not dependent upon the distance or the rho we will take out here, JL KI KJ S nu JL KJ S nu YLM star YLM star KJ the angular part, YLM rho the angular part of rho, and then the differential which is KJ, because if you were to substitute for the wave function then you would see that in the continuity you also get a radial part of the atomic solution. So, you would get Kj times JL prime Kj rho by Kj rho divided by JL times Kj S nu minus RL prime rho divided by RL S nu. So, the thing is that you will have to multiply the two things and integrate. So, what we are now looking for is integral chi 2 I plus chi 1 I times del by del rho chi 2 j minus chi 1 j over the surface of the sphere, which means it is actually sin theta d theta d phi. So, this is the integration that we are going to be carrying out. When we substitute the terms, then we can use the following orthogonality relationships of the spherical harmonics. So, for example, we can show that integral YLM rho y L prime m prime rho sin theta d theta is equal to delta LL prime delta MM prime. That is one relationship that we have, and another relationship that we have is what is called the addition theorem of angular momentum. Also addition theorem of spherical harmonics, which is quite easy to prove. You can look up either on the web, or if you want to look up Powell's book on quantum mechanics. And what this addition theorem says is the following: m is equal to minus L to plus L YLM star Ki YLM Kj, these are all the angular parts, that is equal to 2L plus 1 upon 4 pi PL. It is the angular part of dot product of the two vectors, which is Ki dot Kj. Okay. So, only the angular part of this one. So, if we use these two, and we also use the surface integral is integrating over sin theta d theta. I have taken out d phi because that is going to give me a factor of 2. So, ds the surface integral is going to be S nu ij for the new sphere is minus 4 pi S nu squared e to the I k I j dot r nu times sigma over L is equal to 0 to infinity 2L plus 1 PL Ki Kj, that is the angle between the two vectors Ki and Kj, cosine of the angle between the two vectors, times JL Ki S nu JL Kj S nu multiplied by these derivatives Kj JL prime Kj S nu by Kj S nu JL of Kj S nu minus of RL prime S nu divided by RL S nu. So, the quantities JL prime Kj S nu by JL Kj S nu and RL prime S nu by RL S nu are the logarithmic derivatives. They are the logarithmic derivatives of the spherical Bessel function and the radial function. Once these are evaluated, you have the matrix element Mij is then simply given by Hij plus Sij minus E delta Ij, okay, and this I have already shown you. Let me write it down just again, just for the sake of completeness. Volume of the crystal Kj squared minus E delta Ij plus or minus 4 pi sigma over nu S nu squared e to the I k I j dot r nu times G nu Ij, and G nu Ij was simply what I had written earlier, with G nu Ij being simply k squared Kj squared minus E J1 Kij S nu by Kij minus sigma over L is equal to 0 to infinity 2L plus 1 PL of the angle between the two vectors Ki and Kj times JL Ki S nu and JL Kj S nu. This multiplied by the logarithmic derivatives RL prime RL S nu minus K JL prime Kj S nu by JL Kj S nu. So, once you get the this thing Hamiltonian matrix elements, then it is a straightforward business how to do the this thing obtain the eigenvalues from the Hamiltonian matrix. and the overlap matrix. We set up the generalized eigenvalue problem. H times C is equal to Es times C, where S is the overlap integral, or which we have used in our case as delta, and we can obtain the energies. So this is the crux of the APW method, but in the present day what people are doing is what is called the linearized augmented plane wave methods. In the linearized augmented plane wave method, you fix the value of E prime and you do not vary it, and then you use the functions corresponding to this value of E prime as the basis functions. And what one is doing in the linearized thing is that enhance the basis set, that is, you also use not only UL of R comma E are used as basis, we also use UL dot R comma E, that is del by del R UL R comma E. Dot represents differentiation with respect to the radial variable, the radial coordinate. So this one is also used as a basis. So much so that I can write down phi k n corresponding to any one of the plane wave, augmented plane wave, as sigma over L, sigma over M, ALM, which is a function of times UL R comma E, plus BLM UL dot R comma E times YLMR. So this is used as a basis function, and these are calculated at values which are the energy values. Let me call this EL, because that is the energy value corresponding to RL, and EL is taken to be approximately the energy of the energy at the middle of the case Lth band, at the middle of the Lth band. Well, without doing a band structure calculation, how do you know where the middle of the Lth band is? It is roughly the energy that corresponds to the Lth state eigenvalue of the radial of the equation inside the spheres. So you can actually calculate for that particular value. And they also use a density functional theory using Kohn-Sham equations, and in the Kohn-Sham equation phi kn becomes a basis, and essentially you do a kind of Hartree-Fock solution, except that the potential part is the potential due to the core, that is due to the nucleus, plus U electron interaction part plus a U exchange correlation part. Okay, so and what you are doing is you will make sure that you use this VR as the one that is used in Muffin-Tin potential approximation. Okay, so now I think we will not have a vector notation there. You know, sometimes one can improve upon these calculations by doing what are called APW LO calculations, APW local orbital calculations. This uses the basis function to be slightly different. The basis function it uses is the phi k n local orbital is, let me write it down first and then I will talk about it, ALM UL R comma E L1 plus CLM UL R comma EL2 plus BLM U dot R comma EL1 times YLM R. So, here what you see is we have taken one more orbital UL with energy EL2, which corresponds to the core with energy EL2, and so I expanded the basis in this fashion. So, APW local orbital calculations together with the density functional theory are supposed to give you pretty good energy band structures. Then there is also what is called another thing people do, full Muffin-Tin potential calculations. In the full Muffin-Tin potential calculations, you see that earlier what we did was we took V Muffin-Tin at a particular atom as the center of the atom as nothing but the V at that atom. So, let me call it by different names, V Muffin-Tin V0R plus over all the neighbors I alpha 0 0 0 0 V at R minus Ri, the potentials at the positions which are R minus Ri. So, what we here took was only the L equal to 0, M equal to 0 components. So, we are throwing away contribution of the potential with higher harmonics, higher spherical harmonics to the potential at a particular center. What is done in full potential calculation is in the full Muffin-Tin potentials we consider other components of the spherical harmonics making a contribution. That is, we are also considering things like alpha LM LM are also considered. So, when you do this you lose the spherical nature of the potential. So, you will have to do a numerical calculation to obtain UL R comma EL. We used the notation earlier which was RL, this is not a vector, R comma EL, we use a numerical we use the numerical calculation to obtain UL R comma EL and do a DFT based linear APW, probably with local orbitals. This gives quite accurate band structure. Nowadays you have many ready-made softwares for calculating the DFT based band structures which are floating around, and you can use any one of those to do these calculations. But the important thing is to know how the APW calculations have evolved over the years and how it was first introduced by Slater sometime in 1937. So I think I will stop at this point, and we will continue in the next lecture with another energy band method, the last one that I am going to touch upon, which is the Green's function method for calculating the energy bands, and we will proceed from there to some of the properties of the energy bands in metals. Thank you very much. Bye.